so that I can post this later. Oh, when are grades due? Grades are due for the progress report today by 5. Yeah, and I have posted grades. I don't know if you guys can necessarily see them, but I have posted, like I've already kind of submitted them, but if you want to know exactly what your grade is, just shoot me an email and I will let you know, okay? But that's our progress reports. All right. Perfect. Okay. So let's go ahead and jump into introduction to proofs. So we have 2 different types of reasoning that we see, whether it be in math or be in logic, and those are deductive and inductive reasoning. Deductive reasoning is the one we're kind of going to work through today, but deductive reasoning is basically the process of utilizing facts, properties, definitions, and theorems to formalize a logical argument. So deductive reasoning are basically like things that we know as theorems, definitions, etc. Examples of these may be solving an equation using properties to justify steps, which we're actually going to see today, or they follow the type of statement that we've seen, like all flowers have petals, a rose has petals, so it's justifiable that a rose is a flower. We also have what is known as inductive reasoning. And inductive reasoning is a logical process of making generalizations based on observations and patterns. So inductive reasoning is basically generalizations. They haven't necessarily been proven, but based on the patterns that we've seen, we kind of make that reasoning. So for example, examining a pattern to write a rule, or every quiz has been easy so far, so tomorrow's quiz will be easy. Well, just because every quiz has been easy so far doesn't necessarily mean that tomorrow's quiz will be easy as well. And so inductive reasoning, more cold hard facts, inductive reasoning, more like things we see everyday life, so we just assume that those are facts. Okay, any questions about this? Okay. And so today we're going to get into proofs, and proofs use deductive reasoning. So they use cold hard facts, theorems, which we've seen a couple so far, definitions, etc. Every proof begins with a given. So our given always comes in the beginning, and then it ends with a conclusion. The conclusion is always what we're trying to prove. So for example, you might have already seen a proof where it says, given that so-and-so, prove that something else. So basically you would use a proof to prove that. And then these types of proofs use deductive reasoning as a justification, and we kind of have to justify each step until we get to our conclusion. So may seem a little interesting, but we're actually going to see different types of proofs today. So an example of a proof that we might have already seen is something like this, where we're asked to solve an equation. And you may have seen this in algebra. And there's a specific way that we solve this equation, right? We subtract 4 from each side, then we have to isolate the x, so we divide 3 by each side, and then we eventually get to find what our x is. But what we can do is we can actually create a proof out of this. And so, for example, in order to create a proof, I would have to justify each step until I get to my final answer. So I would always start with my given, which you're always going to name as your given. And then each step has its own proof. So why are we able to subtract? Well, we're able to subtract because of the subtraction property of equality. And then we actually do the subtraction. Why are we able to divide? Well, because of the division property of equality, and then we actually do the division. And then at the end, we always want to end with what we're trying to prove. So we're trying to solve this equation, and so we end with x equals 8/3, which is basically solving this equation. And so basically what you can do is that for anything in math, you can provide a proof. And we're going to look at 3 different types of proofs today. So there are different types of proof formats. The first is a flowchart format, a 2-column format, and a paragraph format. And basically whenever we get proofs in this class, what they're going to look like is you being able to define what this proof is, or to see a proof and then be able to say, oh, that's a flowchart proof. Oh, that's a 2-column proof. That's mostly what we're going to see in this class. But I just want to show you what these things actually are. So a 2-column proof. This is one of the most common proofs that we can see. A 2-column proof is a geometric proof consisting of a list of statements and reasons that we know those statements are true. The statements are listed in a column on the left side, and reasons for which the statements can be made are listed on the right side. So basically, we start with our statements. And as you can see here, we always start with our given. So this would be our given. And then we always end with what we're trying to prove. So we're trying to prove that triangle RSU is congruent to TUS. And so you want to end with that. RSU is congruent to TUS. But what you're doing in these proofs is you're putting reasonings for how you can justify that we can actually prove that given that RSTU in this case is a parallelogram, we can prove that RSU is congruent to TUS. And so two-column proofs split up into two columns, hence two-column proofs, where one side has the statements and the other side has the reasonings. And so that is a two-column proof. So basically, here's just the anatomy of it. We always start with our given, right? We always end with what we're trying to prove. And you always number your steps because you do have a certain number of steps. And then the middle section leads you to your conclusion. So you start with your given, your conclusion, and the middle steps will put each reasoning for how you get to that end proof. So here's an example of a two-column proof, and we're actually going to see how this proof can change depending on what format we're using. And so like before, you always start with your given, and then you always end with what you're trying to prove. And so that's technically the only takeaway you need to get out of this so far. But just know the format. You start with statements on one side, reasonings on the other, two columns, and you always start with your given and end with your conclusion. And then we have what is known as a paragraph proof. Pretty simple. A paragraph proof is basically just a proof written in paragraph form. In other words, it's a logical argument written as a paragraph, given evidence is in the beginning, and then you arrive at a conclusion. So there are different ways you can write this paragraph proof, but again, you always want to start with your given and then end with your conclusion. So as we can see here, it says the given states that, and then whatever your conclusion is. So since we can conclude that, so you always start with your given and with your conclusion. So here, what I did was I took this proof right here and just translated it into a paragraph proof. So we are given the same thing, right? We start with our given, and we can conclude that whatever we're trying to prove, and then all of the steps to which we get to that are in the middle. So this is basically how you would take a paragraph proof, a two-column proof, and create it into a paragraph proof. Okay, and then same thing, start with your given and with your conclusion in all proofs. And then lastly, we have a flowchart proof, which is basically what it is. It's a flowchart. The flowchart proof consisted of a map that shows the statements and reasons needed for the proof and a structure that helps indicate the logical order. Statements written in the logical order are placed in boxes, and then the reason for each of the statement is placed under the box. So we always start with what we're given and then what we're trying to conclude. Same thing here. We start with what we're given, right? We're given this. RS is equal to UV and ST is equal to TU. And then you end with what you're trying to prove right here. Line segment RT is congruent to TV. So same thing, but in this sense, all your different statements appear in boxes, and then we use arrows to connect them, showing where we go from what we're given to what we're trying to conclude. And then if I wanted to create take my paragraph proof or my two-column proof and create a flowchart proof, it would look like this. So always start with what you're given and with what you're trying to prove. Okay? Is there any questions about flowchart proofs, two-column proofs, or paragraph proofs? Questions? And as far as what kind of questions you'll get in this class, is basically being able to define it. May I ask you which of these definitions best describes a flowchart proof, or what is being shown, a paragraph proof, a two-column proof, or a flowchart proof? So those are more likely the type of questions we'll see. Okay. So aside from proofs, I also want to introduce some different properties that we might see in proofs. For example, here we see the symmetric property, the transitive property. So we're going to get into what these actually mean. Okay, So we're going to look at the reflexive property, the symmetric property, the transitive property, and the substitution property. So the reflexive property. A reflexive property basically says that a geometric figure is congruent to itself. Pretty straightforward. Basically, something is congruent to itself. So 1 is equal to 1, 2 is equal to 2. Triangle ABC will be equal to triangle ABC because it's basically the same triangle. So that's what the reflexive property is. It's something is congruent to itself. Okay. The symmetric property, on the other hand, tells us that any term on either side of congruence or equality can be interchanged. So for example, if I said that z is equal to y, well, then I can also say y is equal to z. Basically, you are able to change or interchange those two around, flip them around, and you would still get the same thing. So that's basically what the symmetric property is. The transitive property, on the other hand, is a little bit different, and it states that if two figures are each congruent to a third figure, then those two figures are congruent to each other. So for example, if I said the square was equal to the circle and the square was equal to the triangle, well, because both of the circle and the triangle are equal to the square, well, then I could say that the circle and the triangle are equal to each other. So that's kind of what it looks like. So for example, this one says line segment XY is congruent to line segment MN, and MM is congruent to AB. Well, because I know that these are all congruent to each other, I can assume that XY is congruent to AB as well. So that's kind of what the transitive property would look like. The last one is the substitution property, which we've seen already in algebra before, but basically it tells us if two values are equal, then they're interchangeable in an equation, or if two values are congruent, then they're interchangeable in an equation. What we see most often in this is we are told that, for example, x is equal to 3. Well, if x is equal to 3, I can just substitute x over here into this equation, right? So I'd get 3 plus y equals 12 instead of x plus y equals 12 because I substituted the x for the 3. And so that's what we've seen a lot in algebra. And so that's basically the substitution property. Does anyone have any questions about any of these properties? And I know they take some practice, but any questions so far? Pretty straightforward. Okay. And then the last thing we're going to look at is what assumptions can we make from a diagram? So sometimes we're given a diagram and there's certain things we assume that we can't necessarily assume. For example, I might assume that these two lines, AC and BD, are perpendicular to each other, right? Well, I actually can't assume that. And the reason I can't assume that is because in order for two lines to be perpendicular to each other, they have to intersect at exactly a 90-degree angle. And so the only way I'd be able to assume that is if I had a symbol right here indicating to me that those were 90-degree angles. But because I'm not told that those are 90-degree angles, I can't assume that. But I can assume they're intersecting. I just can't assume that they're perpendicular. So again, there's certain things we can assume and can't assume. So things we can assume is that angles are adjacent. And we'll learn more about what adjacent angles are, but they're basically angles that are right next to each other. We can assume that angles are vertical. We'll learn more about that, but vertical angles are basically opposites of each other. We can assume that things are linear pairs. Basically, there are two angles that share a straight line, and we'll learn more about that as we move on. We can assume that things are collinear points, so they are on the same line. That's something we've already looked at, and we can assume that A and C are collinear because they are on that same line AC. And we can assume that things are opposite rays, which we've looked at before. This would be an opposite ray, and this would be an opposite ray because they are pointing at different directions. Things we can't assume, segment measures. So we can't assume how long this line is without being told exactly how long that line is. We can't assume angle measures. So we can't assume that this is 90 degrees. This could be 91 degrees, or it could be 89 degrees. We can't assume that unless we're given a symbol that's at the right angle to tell us that that's 90 degrees. We also can't assume that lines are parallel because they may intersect at some point unless we're told directly that they're parallel. And we can't assume that lines are perpendicular for the reasoning I just told you. But basically, you can't assume lines are perpendicular unless we are told that they intersect exactly at 90 degrees. Otherwise, they would just be intersecting lines. And we'll work through this as we do some practice tomorrow. But is there any questions right now about why we can assume certain things and why we can't assume other things? Okay. So what did we learn today? Well, we learned about deductive reasoning, but we also learned about inductive reasoning and the difference between the two. But deductive reasoning is basically what we use to create proofs. And we looked at those different proofs today: flowchart proofs, paragraph proofs, and two-column proofs. And then what we got into is different properties for proving different things that we're going to see in geometry, such as a reflexive property, which basically says one thing is congruent to itself. So 1 is congruent to 1, 2 is congruent to 2. We learned about the substitution property, which is the one we kind of see in algebra, which if we know that x equals to 3, then if we have x plus y equals 12, we can substitute 3 for where x is. The symmetric property, we also looked at that one. That's the one that basically if z is equal to y, well then y will also be equal to z. So we can interchange that equation and it would still mean the same thing. And then lastly, we looked at the transitive property, which basically an example is if x is equal to y and y is equal to z, well then x would also be equal to z. And so that's the transitive property. Is there any questions about anything we looked at today? Questions? And like always, we'll go ahead and go over some practice problems tomorrow. But basically, that's the gist of what we're going to look at today. And so if there's no other questions, I will see you guys tomorrow. Bye, guys.